Founder of quantum theory Max Planck is known as the founder of quantum theory because he introduced an idea that fundamentally changed how science understands nature at its most basic level. Before Planck, physics was dominated by classical theories developed by Newton, Maxwell, and others. These theories assumed that energy, motion, and radiation behaved in smooth, continuous ways. For decades, this framework worked extremely well, explaining everything from the motion of planets to the behavior of electricity and magnetism. However, as experiments became more precise near the end of the 19th century, cracks began to appear. One of the most troubling problems was Blackbody radiation. A blackbody is an ideal object that absorbs and emits radiation perfectly. When scientists measured how such objects emit energy at different temperatures, the experimental results did not match classical predictions. Classical physics suggested that as wavelength decreased, the emitted energy should rise endlessly, leading to what was later called the ultraviolet catastrophe. This prediction was physically impossible and contradicted experimental evidence. It became clear that classical physics, despite its successes, was incomplete. Max Planck entered this problem not as a revolutionary, but as a traditional physicist who believed deeply in classical laws. His goal was not to overturn existing theory, but to fix it. While analyzing blackbody radiation data in 1900, Planck made a bold mathematical assumption. He proposed that energy could only be emitted or absorbed in discrete units rather than continuously. These units were proportional to the frequency of radiation and multiplied by a constant, now known as Planck's constant. This single assumption marked the birth of quantum theory. The word quantum comes from the Latin word meaning a fixed amount. Planck suggested that energy comes in fixed packets, or quanta. This idea was radical because it contradicted centuries of scientific thinking. Energy had always been treated as something that flowed smoothly, like water. Planck's proposal implied that at microscopic scales, nature behaves in jumps rather than flows. What makes Planck the founder of quantum theory is not just that he introduced this idea, but that it worked. His formula matched experimental results perfectly. For the first time, the blackbody radiation problem was solved. Yet Planck himself did not fully grasp the revolutionary implications of his discovery. He viewed quantization as a mathematical trick, not as a statement about how nature truly behaves. Even so, the seed had been planted. The true power of Planck's idea became clear when other physicists began to apply it to different phenomena. In 1905, Albert Einstein used Planck's concept of energy quanta to explain the photoelectric effect, demonstrating that light itself behaves as if it is made of particles. This confirmed that quantization was not just a mathematical convenience, but a fundamental property of reality. From that moment onward, quantum theory began to expand rapidly. Planck's role as the founder of quantum theory is also significant because he provided the foundation upon which the entire field was built. Later developments such as Bohr's atomic model, Heisenberg's uncertainty principle, and Schrödinger's wave equation all trace their origins back to Planck's original insight. Without the idea of quantized energy, none of these breakthroughs would have been possible. Despite launching a scientific revolution, Planck remained intellectually humble. He recognized that quantum theory challenged deeply held assumptions about determinism and certainty. Classical physics suggested that if you knew all initial conditions, you could predict the future exactly. Quantum theory replaced this certainty with probability, fundamentally changing the philosophy of science. Planck accepted these changes gradually, even as younger scientists pushed the theory further than he ever imagined. Another reason Planck is considered the founder of quantum theory is his role in legitimizing it within the scientific community. As a respected physicist, his support gave credibility to an idea that initially seemed absurd. His influence helped quantum theory survive early resistance and gain acceptance. Even when he personally struggled with its implications, he defended the importance of following evidence wherever it led. Today, quantum theory is central to modern science and technology. From transistors and lasers to quantum computing and medical imaging, its applications shape everyday life. All of this traces back to Planck's original proposal in 1900. He did not just solve a technical problem, he opened an entirely new chapter in human understanding. In calling Max Planck the founder of quantum theory, history recognizes the moment when physics crossed a boundary. His insight revealed that the universe is far stranger and more complex than classical physics ever imagined. Through one careful, reluctant, yet courageous idea, Planck changed science forever. Crisis of classical physics, the crisis of classical physics at the end of the 19th century, marks one of the most important turning points in the history of science. For more than 200 years, classical physics had been extraordinarily successful. The laws of motion formulated by Isaac Newton explained the movement of planets, projectiles, and machines with remarkable accuracy. James Clerk Maxwell's equations unified electricity, magnetism, and light into a single elegant framework. By the late 1800s, many physicists believed that the fundamental laws of nature were essentially complete, and that future work would only refine measurements to greater precision. Yet beneath this confidence, serious problems were quietly emerging. As experiments became more accurate and explored new domains, certain phenomena stubbornly refused to fit within the classical framework. These failures were not minor details. They exposed deep contradictions between theory and observation. The most troubling aspect of this crisis was that classical physics could not explain behavior at very small scales or very high energies, precisely where new experimental techniques were opening windows into nature. One major source of difficulty was the study of thermal radiation. Physicists investigated how heated objects emit energy in the form of electromagnetic radiation. Classical theories predicted that an object should emit increasing amounts of energy at shorter wavelengths as temperature rose. According to these calculations, a hot object would release infinite energy, an obviously absurd result. This prediction, later called the ultraviolet catastrophe, directly contradicted experimental data, which showed a clear peak and decline in emitted energy. Classical physics failed spectacularly here, and no adjustment within its existing assumptions could fix the problem. Another challenge came from atomic physics. Atoms were known to be the building blocks of matter, yet classical physics could not explain their stability. According to classical electromagnetism, electrons orbiting a nucleus should continuously lose energy and spiral inward, causing atoms to collapse. This clearly did not happen in nature. Matter was stable and atoms persisted, but classical theory had no explanation for why. The behavior of light also added to the growing crisis. Light was well described as a wave in many experiments, such as interference and diffraction. However, certain observations hinted that light did not always behave like a continuous wave. The interaction between light and matter, especially at small scales, produced results that could not be explained by classical wave theory alone. These inconsistencies suggested that the classical picture of reality was incomplete. What made this situation a true crisis was not the existence of unsolved problems, but the realization that the foundational assumptions of classical physics were being challenged. Classical theory relied on continuity, determinism, and precise predictability. It assumed that physical quantities such as energy could vary smoothly, and that the future behavior of a system could be predicted exactly if its present state was known. Experimental evidence increasingly showed that these assumptions were breaking down. Physicists at the time were deeply unsettled. Many believed that the problems could be solved by clever mathematical adjustments or more refined measurements. Few suspected that a radical conceptual shift was required. Max Planck himself initially shared this conservative view. He believed classical physics was fundamentally correct, and that any discrepancies were temporary technical issues rather than signs of a deeper failure. The crisis of classical physics reached its peak around 1900, when repeated attempts to reconcile theory with experiment failed. It became clear that no amount of modification within classical assumptions could explain phenomena like Blackbody radiation. This realization forced physicists to consider ideas that would have seemed unthinkable just decades earlier. The resolution of this crisis began with Planck's introduction of energy quantization. By proposing that energy is emitted and absorbed in discrete units, Planck broke one of the core principles of classical physics. While he initially viewed this as a mathematical convenience, it marked the first step toward a new theoretical framework. Classical physics had reached its limits, and a new theory was needed to describe nature accurately. The crisis of classical physics was ultimately a creative one. It exposed the boundaries of human knowledge and opened the door to quantum theory and later relativity. Rather than destroying physics, it transformed it. The failure of classical ideas forced scientists to rethink concepts such as energy, time, causality, and measurement. In retrospect, this crisis was not a sign of weakness, but of progress. Classical physics remains valid in many everyday situations, but it could not describe the microscopic world. The recognition of its limits was essential for scientific advancement. The crisis of classical physics reminds us that even the most successful theories are provisional, and that scientific understanding evolves through questioning its own foundations. Blackbody radiation problem. The Blackbody radiation problem stands as one of the most important scientific puzzles that led to the birth of modern physics. At first glance, it seemed like a narrow technical issue involving heat and light, but in reality, it exposed a fundamental flaw in classical physics. Understanding this problem is essential to understanding why Max Planck's work was so revolutionary and why classical ideas could no longer explain the natural world. A blackbody is an idealized physical object that absorbs all incoming radiation and emits energy solely based on its temperature. When such an object is heated, it glows and emits electromagnetic radiation across a range of wavelengths. Everyday examples include heated metal, glowing coals, or even the filament of a light bulb. Scientists in the 19th century carefully measured how the intensity of this radiation changed with wavelength and temperature. These measurements were highly precise and remarkably consistent across different materials, suggesting a universal physical law was at work. Classical physics attempted to explain blackbody radiation using well-established principles of thermodynamics and electromagnetism. Two main formulas were proposed to describe the radiation spectrum. One worked well at long wavelengths, while the other matched observations at short wavelengths. However, no single classical theory could explain the entire spectrum accurately. The most serious failure occurred at short wavelengths, where classical theory predicted that the emitted energy should increase without limit. This prediction led to what became known as the ultraviolet catastrophe. According to classical physics, a hot object should emit infinite energy in the ultraviolet region of the spectrum. This result was not just slightly incorrect, it was completely unphysical. Experiments showed that radiation intensity rises to a peak and then falls sharply at shorter wavelengths. Nature clearly avoided the catastrophic behavior predicted by classical theory, and no amount of experimental error could explain the discrepancy. The Blackbody radiation problem was deeply troubling because it struck at the heart of classical assumptions. Classical physics treated energy as a continuous quantity, capable of changing smoothly by any amount. It also assumed that the laws governing large-scale systems applied equally well to microscopic ones. The failure to explain Blackbody radiation suggested that these assumptions might be fundamentally wrong. Max Planck confronted this problem at the turn of the 20th century. His initial goal was not to challenge classical physics, but to find a formula that fit the experimental data. In 1900, after months of struggle, Planck introduced a radical idea. He proposed that the oscillators responsible for emitting radiation could only exchange energy in discrete amounts. Instead of energy flowing continuously, it was emitted and absorbed in fixed packets proportional to the frequency of radiation. This assumption allowed Planck to derive a formula that perfectly matched the observed Blackbody spectrum at all wavelengths. For the first time, theory and experiment were in complete agreement. The ultraviolet catastrophe vanished, replaced by a curve that reflected real physical behavior. The solution worked so well that it could not be ignored, even though it violated classical principles. What makes the Blackbody radiation problem so significant is that its solution required abandoning a core idea of classical physics. The concept of energy quantization was entirely new and deeply unsettling. Planck himself regarded it as a mathematical trick rather than a literal description of nature. He hoped that future developments would restore continuity and preserve classical concepts. However, the success of his formula suggested otherwise. The impact of this solution extended far beyond thermal radiation. By introducing quantized energy, Planck unknowingly laid the foundation for quantum theory. His constant, now known as Planck's constant, became a fundamental parameter of nature. It set a scale below which classical ideas no longer apply and quantum effects dominate. The Blackbody radiation problem also changed the way physicists approached theory. It demonstrated that empirical data could force a revision of even the most trusted assumptions. Classical physics had worked extraordinarily well for centuries, yet it failed when confronted with certain experimental realities. The willingness to accept this failure was a crucial step in scientific progress. In hindsight, the Blackbody radiation problem marks the moment when physics crossed from the classical to the quantum world. It revealed that nature does not always behave in smooth, predictable ways. Instead, at microscopic scales, it operates through discrete processes governed by probabilities rather than certainties. Today, the legacy of this problem is everywhere. Technologies such as infrared imaging, thermal sensors, and even our understanding of the cosmic microwave background rely on principles rooted in Blackbody radiation. What began as a puzzling discrepancy became the gateway to a new understanding of reality. The Blackbody radiation problem did not merely challenge classical physics. It transformed the very language of science and reshaped our view of the universe. Birth of energy, quanta. The birth of energy, quanta, marks one of the most profound shifts in the history of scientific thought. For centuries, Physics was built on the assumption that energy could vary continuously, flowing smoothly like water in a river. This idea was deeply rooted in classical mechanics and electromagnetism, and it matched everyday experience. However, at the dawn of the 20th century, this assumption collapsed, giving rise to a new and revolutionary concept. Energy is not continuous, but comes in discrete, indivisible packets called quanta. This transformation emerged directly from Max Planck's struggle with the Blackbody radiation problem. Classical physics could not explain why heated objects emit radiation in the specific patterns observed experimentally. When Planck analyzed the data, he realized that no classical model could reproduce the measured spectrum. Faced with this failure, he made a bold and unprecedented assumption. The microscopic oscillators responsible for emitting radiation could only exchange energy in fixed amounts, not in arbitrary quantities. Planck proposed that the energy of these oscillators was proportional to the frequency of radiation multiplied by a constant. This constant, now known as Planck's constant, determined the size of each energy packet. The crucial implication of this idea was that energy could not be subdivided endlessly. Instead, it existed in discrete units, much like currency exists in fixed denominations. This was the moment when the concept of energy quanta was born. At first, this idea was shocking and deeply counterintuitive. It contradicted the very foundations of classical physics, which treated energy as a continuous variable. Even Planck himself was uncomfortable with the implication. He viewed quantization as a mathematical device rather than a statement about physical reality. His goal was to match experimental data, not to overturn established theory. Yet the success of his formula made it impossible to dismiss the idea. The birth of energy quanta represented a fundamental change in how physicists understood nature at microscopic scales. It suggested that physical processes occur in discrete steps rather than smooth transitions. This insight challenged long-held beliefs about causality, determinism, and continuity. If energy could only change in fixed amounts, then the classical picture of motion and interaction was incomplete. The true significance of energy quanta became clear when other scientists began to apply the concept beyond thermal radiation. Albert Einstein used it in 1905 to explain the photoelectric effect, showing that light itself behaves as if it is made of discrete energy packets. This interpretation went even further than Planck's original proposal and confirmed that quantization was a fundamental property of nature, not just a mathematical convenience. As the idea of energy quanta gained acceptance, it transformed multiple areas of physics. Niels Bohr applied quantization to atomic structure, explaining why electrons occupy specific energy levels and why atoms emit light at discrete frequencies. These developments solved long-standing puzzles about atomic stability and spectral lines that classical physics could not explain. The birth of energy quanta also forced physicists to reconsider the nature of measurement and observation. In classical physics, systems could be observed without fundamentally disturbing them. Quantum theory revealed that at small scales, the act of measurement itself affects the system. Energy exchanges occur in indivisible units, making precision limits unavoidable. This realization later evolved into principles such as Heisenberg's uncertainty principle. Beyond theory, the concept of energy quanta reshaped technology and society. Modern devices such as lasers, semiconductors, solar cells, and medical imaging systems all rely on quantized energy levels. The digital age, with its reliance on electronic and optical technologies, would not exist without this foundational idea. What began as an abstract solution to a theoretical problem became the engine of technological progress. The birth of energy quanta also carries a deeper philosophical meaning. It reminds us that nature does not always conform to human intuition. The classical view of a smooth, predictable universe gave way to a reality that is granular, probabilistic, and strange. This shift required scientists to accept uncertainty and abandon the comfort of absolute determinism. In retrospect, the birth of energy quanta represents the moment when physics entered the quantum era. It revealed hidden structures in nature and exposed the limits of classical reasoning. Max Planck's reluctant innovation reshaped science forever, showing that even the smallest assumption can lead to the largest revolution. Planck constant h, the Planck constant, symbolized by the letter h, is one of the most important numbers in all of physics. Although it is extremely small, its impact on science is enormous. This constant lies at the heart of quantum theory and marks the boundary between the classical world of everyday experience and the quantum world of atoms and particles. Understanding the Planck constant means understanding why nature behaves differently at microscopic scales. The constant first appeared in 1900 when Max Planck was working on the Blackbody radiation problem. In his effort to match experimental data, Planck proposed that energy could only be emitted or absorbed in discrete packets. He expressed this idea mathematically by stating that the energy of each packet is proportional to the frequency of the radiation. The proportionality factor in this relationship was the constant now known as h. At the time, Planck introduced it as a mathematical parameter with no expectation that it would become a fundamental constant of nature. What makes the Planck constant so significant is that it sets the scale of quantization. It determines the smallest possible units of energy that can be exchanged in physical processes. When the value of h is involved, energy, momentum, and even action are no longer continuous. Instead, they change in discrete steps. The smallness of h explains why quantum effects are not noticeable in everyday life. For large objects, the effects of this constant are negligible, allowing classical physics to work extremely well. As quantum theory developed, the Planck constant appeared in more and more fundamental equations. Albert Einstein used it to explain the photoelectric effect, showing that light consists of particles whose energy depends on frequency. Niels Bohr incorporated it into his model of the atom, where it determined the allowed energy levels of electrons. Later, it became central to wave mechanics, uncertainty principles, and quantum field theory. In each case, h played the same role, defining the limits of classical description. The Planck constant is also deeply connected to the concept of uncertainty. Werner Heisenberg showed that certain pairs of physical quantities, such as position and momentum, cannot be measured simultaneously with perfect precision. The degree of this uncertainty is directly proportional to the Planck constant. This means that uncertainty is not due to experimental limitations, but is a fundamental feature of nature. The constant h thus represents the unavoidable limits of human knowledge at the quantum level. Another profound implication of the Planck constant is its role in wave-particle duality. In quantum mechanics, particles such as electrons behave like waves, and waves such as light behave like particles. The relationship between a particle's momentum and its wavelength depends on h. Without this constant, the dual nature of matter and radiation could not be described mathematically. It acts as a bridge between two seemingly opposite descriptions of reality. Beyond theory, the Planck constant has practical importance in modern technology. Devices such as lasers, transistors, LEDs, and quantum sensors rely on processes governed by H. Even timekeeping systems, such as atomic clocks, depend on energy transitions determined by the Planck constant. In recent years, H has become so fundamental that it is used to define units of measurement, including the kilogram, linking human standards directly to quantum laws. Philosophically, the Planck constant symbolizes a shift in how scientists view nature. Classical physics suggested that the universe could, in principle, be understood completely and predicted with absolute certainty. The introduction of H shattered this belief. It revealed a world governed by probabilities, limits, and discrete events. The constant stands as a reminder that reality has an inherent graininess that cannot be smoothed away by better instruments or deeper theories. Max Planck himself was astonished by the enduring importance of this constant. What began as a numerical factor in a radiation formula became a cornerstone of modern physics. The Planck constant now appears wherever quantum behavior emerges, defining the scale at which classical ideas fail and new rules take over. In the end, the Planck constant is more than just a number. It is a boundary marker between two worlds and a symbol of one of humanity's greatest intellectual revolutions. Through H, Max Planck permanently changed our understanding of nature, revealing that even the smallest constants can hold the deepest truths about the universe. Reluctant revolutionary Max Planck is often remembered as the man who initiated the quantum revolution. Yet one of the most striking aspects of his story is that he was a reluctant revolutionary. Unlike many scientific pioneers who actively challenge existing ideas, Planck did not seek to overthrow classical physics. In fact, he deeply admired it and spent much of his early career defending its principles. His revolutionary contribution emerged not from a desire to break with tradition, but from an unwavering commitment to truth and scientific honesty. During the late 19th century, classical physics was considered nearly complete. The laws of thermodynamics, mechanics, and electromagnetism had explained a vast range of natural phenomena with impressive accuracy. Planck was trained within this tradition and strongly believed in the continuity and determinism of classical theory. He regarded the laws of physics as absolute and universal, reflecting a deep order in nature. For him, classical physics was not just a set of equations, but a world view. When Planck confronted the Blackbody radiation problem, his intention was to preserve classical physics, not replace it. He searched tirelessly for a solution that would fit experimental data without violating established principles. For years, he tried various classical approaches, hoping that the discrepancy between theory and experiment could be resolved within the existing framework. Only when all such attempts failed did he consider a radical alternative. The idea of quantized energy was, for Planck, an act of desperation rather than inspiration. He later described it as an act of despair, a last resort to make the mathematics work. He did not initially believe that energy was truly quantized in nature. Instead, he viewed the assumption as a formal trick that would eventually be replaced by a deeper classical explanation. This hesitation highlights just how revolutionary the idea was, even to the man who proposed it. Planck's reluctance did not end with his initial discovery. Even after his formula successfully explained Blackbody radiation, he remained cautious about its interpretation. When Albert Einstein extended the concept of energy quanta to light itself, Planck resisted the idea. He accepted Einstein's mathematical results, but hesitated to abandon the wave theory of light. This shows that Planck was not eager to push quantum ideas beyond what the evidence strictly required. Despite his personal reservations, Planck demonstrated remarkable intellectual integrity. He published his findings honestly and defended their validity, even when they contradicted his own beliefs. This commitment to evidence over ideology is what ultimately made his work revolutionary. He allowed the data to guide his conclusions, even when they led to uncomfortable truths. Planck's role as a reluctant revolutionary also shaped how quantum theory developed. Because he was cautious and respected within the scientific community, his work was taken seriously. Younger physicists such as Einstein, Bohr, and Heisenberg were able to build upon his ideas precisely because Planck had given them legitimacy. His conservative reputation acted as a bridge between classical and quantum physics. This reluctance also reflects a deeper philosophical attitude. Planck believed that scientific laws reveal objective truths about the universe, independent of human perception. He was uncomfortable with the probabilistic and observer-dependent interpretations that later emerged in quantum mechanics. Even so, he acknowledged that the new theory was necessary to explain experimental facts. His acceptance of quantum theory was slow, but ultimately sincere. The story of Planck as a reluctant revolutionary carries an important lesson about scientific progress. Major breakthroughs do not always come from bold defiance of tradition. Sometimes they emerge from careful, methodical work carried out by those who respect existing knowledge, but are willing to revise it when reality demands. Planck did not abandon classical physics lightly. He did so only when evidence left him no choice. In the end, Max Planck's reluctance does not diminish his achievement. On the contrary, it makes it more powerful. His journey shows that true revolutions in science are driven not by rebellion, but by honesty, discipline, and respect for truth. By following the evidence wherever it led, even against his own instincts, Planck became one of the most important figures in the history of science. Resistance from the scientific community, the revolutionary ideas introduced by Max Planck, did not sweep through the scientific world with immediate acceptance. On the contrary, they were met with significant resistance from the scientific community. This resistance was not driven by ignorance or stubbornness alone, but by the deep success and intellectual comfort provided by classical physics. Planck's work challenged ideas that had been trusted for centuries, and such challenges rarely go unopposed. At the turn of the 20th century, classical physics was the foundation of scientific understanding. It had explained planetary motion, mechanical systems, heat, electricity, magnetism, and light with extraordinary precision. Many leading physicists believed that the fundamental laws of nature were already known. In this environment, the suggestion that energy could be emitted in discrete units seemed unnecessary and even absurd. To many, Planck's quantization appeared to violate the principle of continuity that lay at the heart of physics. One reason for the resistance was the lack of direct experimental evidence for energy quanta. Planck's idea emerged from a mathematical solution to Blackbody radiation, not from an experiment that directly observed quantized energy. Many physicists viewed it as a clever calculation rather than a physical reality. They hoped that a classical explanation would eventually be found, rendering the quantum assumption unnecessary. Even Planck himself contributed to the cautious reception of his idea. He initially presented quantization as a formal hypothesis, not as a claim about the true nature of energy. His hesitation gave others reason to treat the concept with skepticism. If the originator of the idea was uncertain, many saw no urgency in embracing it fully. The resistance grew stronger when quantum ideas began to spread beyond Blackbody radiation. Albert Einstein's explanation of the photoelectric effect, which treated light as consisting of discrete particles, faced even harsher criticism. Light had long been understood as a wave, and wave theory had been spectacularly successful. The idea that light could behave like a particle contradicted deeply held beliefs. Even prominent scientists rejected Einstein's interpretation, including Planck himself, who supported the mathematics but resisted the physical implications. Generational differences also played a role. Older physicists, who had built their careers on classical theory, were naturally hesitant to accept ideas that undermined their life's work. Younger scientists were more open to radical concepts, but they often lacked the authority to influence mainstream opinion. This divide slowed the acceptance of quantum theory and fueled debates that lasted for decades. Philosophical concerns further intensified resistance. Classical physics was deterministic, offering a universe governed by precise laws and predictable outcomes. Quantum ideas introduced probability, uncertainty, and discontinuity. Many scientists found this deeply unsettling. The notion that nature itself might be probabilistic seemed like a retreat from scientific certainty. Critics argued that quantum theory was incomplete or temporary, expecting it to be replaced by a more satisfying classical explanation. Despite this resistance, evidence continued to accumulate in favor of quantum ideas. Experiments on atomic spectra, specific heat, and radiation all supported quantization. Slowly, the scientific community began to recognize that classical physics could not account for these results. Resistance gave way to cautious acceptance and eventually to widespread adoption. Max Planck played a crucial role during this transition. Although hesitant about some interpretations, he consistently defended the importance of confronting experimental facts. As a respected authority, his support helped legitimize quantum research. He also encouraged younger physicists, providing them with opportunities to develop and refine the new theory. The resistance from the scientific community ultimately strengthened quantum theory. It forced physicists to test ideas rigorously, refine their arguments, and gather overwhelming evidence. The intense scrutiny ensured that quantum theory was not accepted lightly, but because it worked where classical physics failed. In retrospect, this resistance illustrates an important truth about science. Revolutionary ideas rarely gain immediate acceptance, especially when they challenge deeply rooted assumptions. The struggle faced by Planck and his successors shows that progress often requires patience and persistence. What was once dismissed as radical and implausible is now foundational, reminding us that scientific truth is not decided by comfort or tradition, but by evidence and reality. Influence on Einstein and modern physics, Max Planck's work did not merely solve a technical problem in physics. It became the cornerstone of an intellectual revolution that shaped the entire 20th century. One of the clearest measures of his influence is the way his ideas inspired Albert Einstein and ultimately transformed modern physics. Without Planck's groundbreaking insight into quantized energy, the developments that followed quantum mechanics, relativity, and much of modern technology might have been delayed or taken a very different path. Understanding Planck's influence requires exploring both the intellectual context of his time and the chain of discoveries his ideas set in motion. At the end of the 19th century, classical physics had achieved remarkable successes, but it was showing cracks. Planck's work on Blackbody radiation introduced the radical idea that energy is quantized, coming in discrete units proportional to frequency. Initially, Planck himself did not fully appreciate the revolutionary implications of this concept. He saw it as a mathematical convenience rather than a fundamental property of nature. Nevertheless, the mere proposal of energy quanta planted a seed that other physicists would cultivate, particularly Albert Einstein. Einstein's genius lay in his ability to see the broader implications of Planck's discovery. In 1905, he applied Planck's concept of energy quanta to explain the photoelectric effect. Experiments had shown that light shining on certain metals could eject electrons, but classical wave theory could not account for the observed results. The ejection depended on the frequency of light, not its intensity. Einstein proposed that light itself consists of particles, or photons, each carrying energy proportional to its frequency, exactly following Planck's formula. This bold extension of Planck's idea provided compelling evidence that quantization was a real feature of nature, not just a theoretical trick. In this way, Planck directly influenced one of Einstein's most significant breakthroughs, which later earned him the Nobel Prize in Physics. Planck's influence extends far beyond Einstein's work on the photoelectric effect. The introduction of quantization laid the foundation for the entire field of quantum mechanics, which redefined our understanding of matter and energy. Niels Bohr, inspired by Planck's ideas, proposed that electrons occupy discrete energy levels in atoms, explaining the observed spectral lines of hydrogen. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed the mathematical framework of quantum mechanics, relying heavily on the notion that physical quantities are fundamentally quantized. Every one of these major breakthroughs traces its roots back to Planck's insight, illustrating the profound and lasting impact of his work. The influence of Planck's ideas was not confined to atomic and subatomic phenomena. His concepts also played a crucial role in understanding radiation, heat, and even cosmology. The Planck constant became a central element in describing energy, momentum, and angular momentum at microscopic scales. Quantum field theory, quantum electrodynamics, and other advanced theories all incorporate Planck's constant as a fundamental parameter. Without it, modern physics would lack a unifying thread to connect microscopic and macroscopic phenomena. In addition to influencing theory, Planck's work reshaped scientific methodology. By showing that empirical discrepancies could necessitate radical conceptual changes, he encouraged physicists to question assumptions that had long been considered immutable. Einstein famously acknowledged this intellectual debt, stating that Planck's work provided the starting point for the revolution that led to relativity and quantum theory. In effect, Planck taught physicists that even the most established principles could not stand against experimental evidence. The broader implications of Planck's influence are evident in the technological transformations of the 20th and 21st centuries. Quantum mechanics, built on the foundation of energy quanta, underpins semiconductors, lasers, magnetic resonance imaging, and quantum computing. Planck's ideas indirectly shaped the digital revolution, telecommunications, and modern medicine. Without his initial insight, many technologies that define our lives today would be impossible. Philosophically, Planck's influence challenged the deterministic worldview of classical physics. Einstein himself grappled with the probabilistic nature of quantum mechanics, famously remarking, "God does not play dice." Planck's quantization revealed that at the microscopic level, the universe is inherently discrete and governed by probabilities, a radical departure from the predictable, continuous world described by Newton and Maxwell. This conceptual shift continues to influence how scientists and philosophers think about reality, knowledge, and the limits of human understanding. Planck's influence on Einstein and modern physics illustrates the power of a single insight to transform human thought. By daring to propose that energy is quantized, Planck opened a pathway to a new understanding of nature, one that reshaped physics, technology, and philosophy. Even though he approached his discovery with caution and modesty, the impact of his ideas has been immense, guiding generations of scientists and forming the backbone of contemporary physics. In conclusion, Max Planck's influence on Einstein and modern physics cannot be overstated. He provided the first crucial insight that challenged classical assumptions and paved the way for a new scientific era. By introducing the concept of energy quanta, Planck not only solved a pressing experimental problem, but also inspired revolutionary ideas that reshaped our understanding of the universe. From atomic theory to quantum mechanics, and from fundamental research to transformative technologies, the legacy of Planck's influence endures as a testament to the power of bold, evidence-driven thinking. Philosophy of science and reality, Max Planck was not only a brilliant physicist, he was also a deep thinker about the nature of science and the limits of human knowledge. His contributions to physics were inseparable from his philosophical reflections on how science uncovers reality, the role of theory, and the relationship between evidence and belief. Planck's philosophy of science, shaped by his revolutionary work on quantum theory, continues to influence how scientists and philosophers approach the natural world. Exploring this keynote helps us understand not only Planck's scientific achievements, but also his intellectual worldview. Planck believed that the ultimate goal of science was to uncover objective truths about the universe. He regarded natural laws as universal, immutable, and discoverable through careful observation and reasoning. However, unlike many of his contemporaries, Planck understood that these truths could never be fully captured by a single generation of scientists or by any one theoretical framework. In his view, scientific knowledge evolves gradually, sometimes in small steps, and occasionally in dramatic leaps. The quantum revolution itself illustrated this principle. A centuries-old framework of classical physics was appended by new ideas that emerged slowly, cautiously, and sometimes reluctantly. One of Planck's most famous philosophical statements is his observation that science advances one funeral at a time. By this, he meant that deeply ingrained scientific beliefs often survive until their adherents pass away, and new ideas gain acceptance primarily through younger generations who are more open to change. This remark reflected both his humility and his realism about human resistance to paradigm shifts. It also demonstrated his understanding of the social dimensions of scientific progress. Discoveries are not judged solely on logic or evidence, but are filtered through human culture, psychology, and institutional authority. Planck's reflections on the philosophy of science were closely tied to his work on quantum theory. The discovery of energy quanta challenged the classical notions of continuity, determinism, and predictability. For centuries, physics had assumed that the universe operated like a clock, with every cause producing a precise effect. Quantum mechanics introduced probability, discreteness, and fundamental uncertainty into this picture. Planck's philosophical outlook allowed him to accept these implications gradually. He saw that science must follow evidence, even when it undermines cherished assumptions. This approach exemplifies a key principle of scientific philosophy: the commitment to truth over comfort or tradition. Another dimension of Planck's philosophy was his understanding of the limits of human knowledge. He recognized that even the most elegant theories are provisional and subject to revision. Classical physics worked extremely well in everyday contexts, but failed at atomic and subatomic scales. Planck's insight into quantization revealed that nature is far stranger than everyday experience suggests. This recognition instilled a sense of humility. Science is a journey toward understanding, not a repository of final truths. Theories are tools to model reality, not exact replicas of it. Planck also appreciated the interplay between mathematics and physical reality. In his work on Blackbody radiation, he relied on mathematical techniques to solve experimental puzzles. He understood that mathematics is a language to describe observations, but it is not reality itself. This distinction was central to his careful philosophical stance. Even when the equations implied radical consequences, such as quantized energy, Planck remained cautious about claiming direct physical interpretation until evidence demanded it. This measured approach illustrates the balance between theoretical innovation and empirical grounding that he advocated. The philosophy of science, according to Planck, also emphasized the importance of intellectual honesty and rigor. He believed that scientists must confront experimental evidence objectively, even when it contradicts personal beliefs or established doctrine. His own reluctance to immediately embrace the full implications of quantization shows that a responsible scientist can question ideas without rejecting reality. By following the data where it leads, Planck exemplified the ideal of scientific integrity, respect for nature over personal or institutional preference. Planck's reflections extend beyond physics to broader questions about reality itself. By introducing quantization, he demonstrated that the universe operates in discrete steps at a fundamental level, challenging intuitive notions of continuity. This has philosophical implications for how we perceive causality, determinism, and the nature of matter and energy. Planck's work invites us to reconsider assumptions about reality, suggesting that it is far more intricate, probabilistic, and layered than our everyday observations indicate. Moreover, Planck's philosophy emphasizes the human aspect of science. Discoveries do not occur in isolation. They emerge from a community of thinkers, experiments, and debates. Resistance, skepticism, and gradual acceptance are natural parts of this process. Planck himself navigated these dynamics, contributing not only through equations, but also through mentorship, dialogue, and engagement with the scientific community. His philosophical approach demonstrates that science is both a mental and social endeavor, shaped by evidence, reasoning, and human judgment. In conclusion, Max Planck's philosophy of science and reality reflects his unique blend of intellectual rigor, humility, and ethical responsibility. He recognized that scientific progress is gradual, that theories are provisional, and that reality often defies intuitive expectations. By combining empirical rigor with deep philosophical reflection, Planck modeled a way of understanding nature that balances innovation with caution, curiosity with skepticism. His insights remind us that science is not merely about discovering formulas, but about seeking truth, embracing uncertainty, and continually refining our understanding of the universe. Planck's philosophical legacy, therefore, is inseparable from his scientific legacy. It shaped how quantum theory emerged, guided how subsequent generations approached foundational questions, and continues to inform the ways we think about reality, evidence, and the pursuit of knowledge. His work stands as a testament to the idea that science is both an empirical and philosophical endeavor, and that understanding the universe requires both mathematical insight and thoughtful reflection. Lasting legacy in the quantum age, Max Planck's contributions to physics did not end with his own lifetime. They created a legacy that continues to shape the modern world. Known as the father of quantum theory, Planck's work fundamentally altered how humanity understands energy, matter, and the laws governing the universe. His discoveries not only resolved the specific problem of blackbody radiation, but also opened the door to entirely new fields of research, technologies, and philosophical insights. The lasting impact of his work is evident in science, technology, education, and even culture, making him one of the most influential figures in the history of human thought. Planck's immediate scientific legacy was the establishment of quantum theory. Before his work, classical physics dominated scientific understanding. Newtonian mechanics, Maxwell's equations, and thermodynamics provided a framework that seemed nearly complete. However, certain phenomena, such as blackbody radiation, the photoelectric effect, and atomic spectra, could not be explained within this framework. Planck's proposal that energy is quantized solved these puzzles and laid the foundation for a new understanding of the microscopic world. The introduction of energy quanta and the Planck constant h became essential elements of all subsequent quantum research. The development of quantum mechanics in the decades after Planck's work relied on the concepts he introduced. Niels Bohr used quantization to explain atomic spectra, showing that electrons occupy discrete energy levels. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built on these ideas to formulate the mathematical framework of quantum mechanics. Today, quantum mechanics is not just a theoretical exercise. It is a cornerstone of physics that describes the behavior of matter and energy at the atomic and subatomic scales. Without Planck's original insight, this entire intellectual structure would have been impossible. Beyond theoretical physics, Planck's legacy extends into technology. Quantum mechanics underpins countless devices that define modern life. Semiconductors, the heart of computers and smartphones, operate based on principles of energy quantization. Lasers, which rely on precise quantum energy transitions, power everything from medical instruments to telecommunications. Magnetic resonance imaging MRI, solar panels, and LED all depend on quantum principles rooted in Planck's work. In this way, Planck's ideas transformed society by enabling technologies that touch every aspect of human life. Planck also influenced the way science is practiced. His careful, methodical approach, combined with his respect for evidence, serves as a model for scientific inquiry. He was cautious yet open to revolutionary ideas, demonstrating that great breakthroughs often emerge from disciplined observation rather than bold speculation alone. His insistence on following evidence, even when it contradicted intuition or long-held beliefs, exemplifies the principles of scientific integrity. This approach continues to inspire researchers in physics and beyond. Another aspect of Planck's legacy is philosophical. By introducing quantization, he challenged the deterministic world view of classical physics. Quantum theory revealed that at microscopic scales, events are probabilistic rather than strictly predictable. This reshaped not only scientific thought, but also philosophical discussions about reality, causality, and the limits of human knowledge. Concepts such as uncertainty, probability, and duality, all rooted in Planck's discoveries, have changed how humanity understands the natural world. Planck's influence is also seen in education. Physics curricula around the world teach quantum mechanics as a central subject, beginning with Planck's work on blackbody radiation. Students learn about the Planck constant, energy quanta, and quantization as foundational concepts. In this sense, Planck's ideas continue to shape the minds of new generations, ensuring that his legacy is both intellectual and pedagogical. Even culturally, Planck's contributions have left a mark. The term Planck's constant has become synonymous with the quantum revolution. His story is cited as an example of scientific perseverance, humility, and the transformative power of ideas. Documentaries, books, and lectures celebrate his life, ensuring that his achievements are accessible not just to scientists, but to the general public. Planck's legacy also serves as a reminder of the nature of scientific progress. His discovery was not immediately accepted. It faced resistance from the scientific community. Yet, over time, the validity of his work became undeniable. This process illustrates a key lesson. True scientific innovation often requires patience, rigor, and the courage to follow evidence wherever it leads. Planck's experience shows that even a single insight, carefully explored, can transform human understanding. In the broader context of modern physics, Planck's work continues to influence cutting-edge research. Quantum computing, quantum cryptography, and particle physics all rely on principles first suggested by Planck. Cosmology and the study of the early universe also depend on quantum concepts, linking his legacy to our understanding of the cosmos itself. The scale of Planck's impact is extraordinary. From the tiniest particles to the largest structures in the universe, his ideas remain foundational. In conclusion, Max Planck's lasting legacy in the quantum age is immense and multifaceted. He provided the initial spark that ignited quantum theory, influenced generations of scientists, transformed technology, and reshaped philosophical understanding of reality. His discoveries continue to shape education, research, and society at large. By challenging classical assumptions and following the evidence wherever it led, Planck not only solved specific scientific problems, but also transformed humanity's conception of the universe. Today, the quantum world, with all its strange and fascinating properties, stands as a testament to the enduring power of Planck's insight, a legacy that will continue to inspire and guide humanity for generations to come.